This is always a conjecture about what the model is. So the choice of a straight line or for the signal component is consistent with the knowledge of that Dow Jones average is hovering around 3,000, and then A is is the uh, fixed constant that models this, and then the conjecture that the conjecture that it is increasing. So this is the slope, right? So the slope B, and this is assumption of why Gaussian noise is justified by the need to formulate a mathematical tractable model. Right? Mathematical tractability is also important. So the closed form estimators can be found. Also, it is reasonable unless there is strong evidence to the contrary, such as highly correlated noise. Of course, the performance of any estimators obtained will be critically dependent on the PDF assumptions. We can only hope that estimator obtained is robust, in that slight changes in the PDF do not severely affect the performance of the estimator. So this is kind of the philosophy that we are using. But again, we are not assuming that we know the absolute truth about the physical systems. Okay. Okay. So estimation based on PDF such as this is termed as a classical estimation. In that, the parameters of interest are assumed to be deterministic but unknown. Deterministic, unknown. And then there are other possibilities for the parameters. Okay, so it seems inconsistent with reality that to choose an estimate of A that result in values as low as 2,000 or 4,000. We might be more willing to constrain the estimator to produce values of A in a range. So for example, A is not treated as deterministic, it's treated as in a range. Then what that means is we have a prior knowledge about A is roughly somewhere. And to incorporate this prior knowledge, we can assume that A is no longer deterministic. It's no longer deterministic, but a random variable. It's a random variable and assign it a PDF. Remember that whenever we have a random variable, uh, it has a PDF. So uh, any subsequent estimator will yield values in this range. Such an approach is termed Bayesian estimation, and it could be possibly uniform over the range. Okay, the parameter we are attempting to estimate is then viewed as a realization of a random variable, theta. As such, the data are described by the joint PDF. It's a joint PDF and it has a P of theta. Now it has a prior. So imagine if it's deterministic but unknown, then you will not be able to have this P theta. But if you treat it as a random variable, then it can be written in Px conditional theta multiplied by P theta. So P theta is now the prior PDF, and that PDF is summarizing our knowledge about theta for any data are observed. Notice that the P of theta is prior, it has no relation to uh, even before or after you receive data, right? This term It's by itself. It has nothing to do with X, right? Its dependence on X will be summarized by this term, but P of theta is prior by itself. Okay, so summarizing our knowledge about that before any data are observed. And P of X data is a conditional PDF. Summarizing our knowledge provided by the data X conditioned on knowing theta. Okay, so I think the relation between X and parameter theta still exists, but it's summarized in this term. Okay, so let's continue. Once the PDF has been specified, the problem becomes one of determining an optimal estimator or a function of the data. Recall that we talk about estimator is a function of data. Note that an estimator may depend on other parameters, but only if they are known. An estimator may be thought of as a rule that assigns a value to theta for each realization of X. It's a function of X, or you think of it as a rule that assigns a value to X, to theta, for each possible values of X. The estimate of theta is the value of theta obtained for a given realization of X. Okay? And then we go to the next session, which is to assessing assessing estimator performance. Consider the data set from a cursory inspection appears that Xn consists of the DC level A in noise. The use of term DC is in reference to direct current. So oftentimes we have something fixed as a constant level. We call it a DC level. We could model the data as something like this. So this is the example. If you have a Xn that goes like this, it looks like you have some kind of DC level being immersed in noise. So that is the DC level in noise. Wn denotes some zero mean noise process. Okay, it's zero mean noise process. Based on the data set x0, x1 to xn minus 1, we would like to estimate A. Intuitively, since A is the average level of xn, it would be reasonable to estimate NA as something like this, right? So let's say you have A, you have this model and you observe xn, you want to estimate A. What you want to do is, this is just one of the options. Okay, one of the options. A hat equal to n divided by n, summation of xn. Okay, so just take the average. Or this is the sample mean of the data. Okay, once you come up with the estimator, with that estimator A, then you start to wonder a couple questions. Several questions come to mind. How close will A hat be to the true value of A? Right? This is an important question. And then, are there better estimators than the sample mean? This is trivial because we use it very often. So we kind of take it for granted. But well, in fact, you have a lot of different choice. You have a lot of different choice. So uh, for the data set, it turns out that A hat is zero point 0.9, which is close to the true value A equal to 1. And then another estimator might be like this, right? Oh, then you see this, you will say, well, you have a lot of samples, right? You have like maybe 100, 1,000 samples. Then why are we only using one, right? For this XA uh, equal to X0, we are using only one sample, and it could look very strange or even very naive when you first see it. But think about this. Think about this. If you are using this one, you are using only one sample. Use this one, you could be using 100 sample. But it looks like intuitively this A hat could be better than that. But if you think about the cost, it uses X0, which is just one sample. The cost, we think about the cost. The cost is actually lower for this one. It has higher cost. So, uh, different estimators may have different advantages and disadvantages. It's not like one criteria or one standard that fits everybody. It has a different perspectives and different standards. So, uh, uh, but here, if we are asking how close will it be, then we are asking about the accuracy. Okay, so intuitively, we will not expect this estimator to perform as well, since it does not make use of all the data. There is no averaging to reduce the noise effects. However, for the data set A delta is 0.95, which is closer to the true value of A than the sample estimate. So this is a coincidence. A coincidence. Then can we conclude that A delta is better than estimated A hat? The answer is not. Then later we will discuss how come it's not. For a specific case, it could be, but for the general case, it may not be. Because the estimator is a function of data, which is random variables. It is very important to notice this. It's very important to notice this because an estimator is a function of data, and data before you take the observation is random variable. So if you are taking a function of a random variable or function of random variables, then the outcome will be random variable. So it's a random variable subject to many possible outcomes. The fact that A delta is closer to the true value only means that for that given realization of data, the estimate, which is a realization, is closer to the true value than the estimate, the realization of A hat. To assess performance, we must do so statistically. Statistically. Okay. So one possibility would be to repeat the experiment that generated data and apply each estimator to every data set. Then we will ask which estimator produce a better estimate in majority of the cases. But it will be impossible for us to realize infinite amount of cases, right? Infinite is impossible. So, uh, so we do it statistically. What we do is we do a lot of them, but not infinite. So, uh, we plot a histogram. We plot a histogram. So, uh, for 100 realizations, the histograms are shown in figure. So we will see. So it should be now be evident that A is a better estimator than A delta because the values obtained are more concentrated about the true value. Okay, so let's take a look. We try to realize this A hat and A delta. This is a sample mean, and this is the first sample. And realize a lot of times and do the histogram. Histogram is kind of a approximation for the distribution. Recall that this is a estimator, right? Estimator. It is also a random variable. We have to emphasize this. Again, this is the estimator and also a random variable. And then, because for a random variable, we will be able to talk about its distribution. If an estimator is not a random variable, then we will not be able to talk about its probability density function. So we talk about uh, histogram. We talk about histogram, and then using histogram as an approximate for the distribution. Now we see this is closer concentrated to true value, and this is widespread. Widespread meaning that you have a lot of chances of going out of it, going further away from the true value, and this is more concentrated. As a result, as a result, we will see that uh, A hat will usually produce a value closer to the true one rather than A delta. And then some people might be skeptical about this and say, if we repeat 1,000 times or 10,000 times or even more, how would the histogram be? Would it still be more concentrated? We'll ask that question. So we do further investigation. We cannot repeat uh, infinite amount of time. Technically, right? Infinity is impossible for us to produce. So to prove that A hat is better, we establish that the variance is less. So uh, the modeling assumptions that we must employ are that the Wn in addition to bin zero mean are uncorrelated and have equal variance sigma square, which is often true. Then we show that the mean of each estimator is true value, or we see that first thing is we take the expectation. The expectation of A hat, then you take the expect of this and then expect goes in, so 1 divided by n, then summation of expect xn. Xn is all a, right? Xn is equivalent to a, and a, you sum it over n times, it becomes na, and na divided by n becomes a, and a hat is expect of one single data, which is a. What that means is this expect of the estimator goes to a, expect of that estimator also goes to a, and so that on average the estimator produce the true value. On average, we're talking about on average. Second, the variances are, you take the variance and then variance of this whole thing equal to n squared, and then summation variance of that is n sigma squared. As a result, you get sigma squared over n. And then since the Wn's are uncorrelated, and that's variance a hat is variance x0, which is sigma squared. So if you compare variance of this variance and that variance, this guy a hat produces sigma squared over n, and the other estimator produce sigma squared. Sigma squared is larger than that, right? This is larger than sigma squared over n. Therefore, we will say that a hat has smaller variance. Smaller variance. So if we look at the figure again, we say that this one, we have proved analytically this one has smaller variance. And the smaller variance will tell us that a hat is in fact statistically closer to the true value 1. Okay, so yeah. Furthermore, if we assume that Wn is Gaussian, we could also conclude that the probability of given magnitude error is less for a hat than for a delta. So several important points are illustrated by this example, which always be kept in mind. An estimator is a random variable. As such, its performance can only be completely described statistically or by its PDF. And then, of course, we can use some computer simulations to repeat a lot of things. Okay, so that's the end of this session.